better with the microphone on. We will be exploring further aspects of the IP layer, in particular the addresses. Those seems to be trivial aspects, but if we don't know them well, they are in our way. So in some sense, it's a painful but easy set of details that we have to analyze. So we'll talk about host configuration to start with. As you have already observed in the first labs, it's not enough to have an IP address for an interface. You also need to have the mask that we've discussed in the past weeks, but also things like the IP address of the default router, if there is a router, which is the normal case, and also the IP address of the DNS server. So that's the minimum set of 4 informations that you need to have with IP. We will see that if we compare with the MAC layer, in the MAC layer, there is no configuration that you need. So the MAC layer is plug and play, but IP is not in that sense here. We've seen how to do that manually, but of course it's not very nice. So what we will see today is how it is typically done with DHCP, and you have variants of DHCP, PPP, for example, that we will discuss that are not very exciting and give essentially the same. So what happens when a computer boots? And by default, it's configured to use DHCP, which is probably what happens on most computers by default. Then this computer does not have yet an IP address. And it is connected to some network, a Wi-Fi base station, or an Ethernet system somewhere. On this network, there is certainly one or several routers. So the idea of DHCP is to have a server that is able to allocate addresses by choosing a block of addresses that correspond to each subnetwork that is identified by a port or an interface or on a router. So typically, you have a central server. If you're at home, you have simply your ADSL modem or your Cablecom modem that will do the DHCP function. If you're in a larger organization, like EPFL, you don't want to have one server per router. Therefore, you will have what is called a trick, which is called a relay, DHCP relay, where this router here will simply pass on all the DHCP requests from hosts. So let's have a look at what those requests are. When your system boots, it sends a query saying, I would like to get an IP address, and I pass on what is my MAC address. Typically, the IP address might be linked to the MAC address. And if there is a DHCP server in this box, I mean, this packet with IPv4 is sent to this address, which you recognize as what special address is this? Broadcast. That means that this is sent to all systems in the subnetwork. The MAC address will therefore also be the MAC broadcast address. And with IPv4, this will be received by all systems, and hopefully one of them is a DHCP server or relay. If it's a relay, if it's a server, that's the end of it. That's the case at home. It will simply respond by giving an IP address. And in order to make sure that the transaction is really committed, you have a second confirmation to handle the cases where any of the packets might be lost. The MAC address might be used to screen the addresses here. You might want, for example, to not allow some systems. You may have a very strict rule at home. You say, here are the machines that I accept to have in my network. So you look at all their MAC addresses, and you can accept the machines based on their MAC addresses or not. If you play with a modem at home, you will find in the configuration somewhere the ability to do so. This is also used to what is called fix an address. If you have a machine that you would like that it always keeps the same address, because you have a server, for example, on it, then you may still use DHCP, but in your DHCP server, you may tick a box somewhere saying this machine that is known by this MAC address must have this IP address. So we use MAC addresses because those are the only addresses that come by the hardware that don't require configuration. If you're in a larger setting, the same happens, except this box here will simply pass the information to a server that will send it back. So this is a router. It has an IP address. It knows how to speak to this. This DHCP v4 server is an application server from the viewpoint of the TCP-IP layer. It's an application server, and the IP address of this is configured in this one, so it knows how to talk to this one. It will simply forward the message saying, I am this router with my IP address. I have a client that asks for an IP address on this interface. Please tell me which address I should give if this is allowed. This is, as usual in TCP/IP, anything that you do in principle should have a finite lifetime. This is to avoid deadlocks. So this address is given for some amount of time, a few tens of minutes or a few hours, so that if a system disappears, the address is released and is not used up forever. About terminology, we say a router is a DHCP relay. This is an overloading of terminology. If we want it to be very accurate, I would say the box that I have here has several functions. One of them is to be a router. Another one is to be a DHCP relay. Those are, from the layering viewpoint, if you like that kind of terminology, those are different functions. But DHCP relays are invariably installed in boxes that are also routers. You have variants of that. For example, your ADSL modem that is connected to Swisscom, for example, has the same problem. When it boots, it needs to obtain an IP address from Swisscom. So it can use DHCP. Very often this is done indeed. Sometimes something else is used, which is a PPP, which is essentially the same, just it's older and the name is a bit different. This is that's the end of the story for IPv4. So we could move on to section 7. For IPv6, unfortunately, there are zillions of microscopic details that have been added. This is an example of, since we have a very large address space, the complexity is now only limited by human beings. So everybody has invented a way to use IPv6 in their own way, and by opening the space, we have just made the thing more complex. We'll see an example here about address allocation. You could say with IPv6 you do the same as IPv4, either manually or with DHCP. But that's not the case. There is a whole range of intermediate things, and one that is very often used is called SLAC, or SLAC, stateless address auto-configuration. Well, the idea seems like a good idea, but as we'll see, it's a bit complicated, is that hosts should be able to discover their address automatically. And the idea is very simple. I mean, if you're a host and you start on a network, on this network there is a router. The router has been installed by someone. We find in general that there is a dichotomy of management of devices. Hosts, PCs, smartphones, they should be entirely plug and play and usable. They're used by anybody. There should be no configuration to do. The routers, the ADSL boxes, you typically need a small bit of configuration to do. So when you're a host and you start on a network, there is probably a router on this network. If there is no router on this network, this will be an isolated network, and you can use a linked local address. There's not much to do. If there is a router, you could speak to this router to get all the information you need instead of speaking to a DHCP server. Why is there this difference? Well, the idea is that if the address space is large enough, what is an IP address made of from the viewpoint of a host, of a final system? It's made of a prefix, which says where you are on the internet, and a host part. And the goal of DHCP is to provide you those two informations. What is your prefix? Also the network mask, which indicates which part of the IP address corresponds to the prefix, and your host part. But now, if you talk to a router, the router knows the prefix on which the link is, because the router is already configured. So the router can tell you what is the prefix. The only thing that the router cannot tell you is what is the host part. In IPv4, the host part is typically a few bits, 6 to 8 bits typically. So on a large network, there might be a problem of collisions. If you allow systems to pick whatever host part they like, there might be collisions because we have only 100, 200 possible host parts. This is why in IPv4, typically we have DHCP. In IPv6, with 128 bits, what is very often done is the host part is 64 bits. So the host part is in fact larger than the MAC address. So one simple idea is use your MAC address as your host part, ask the router for the prefix and the subnet mask to verify it's really 64 bits or something else. And then the two together give you the address. You don't need DHCP for that. And to make a long story short, this is what Slack is doing. Exactly. Slack is in fact originating from the Macintosh AppleTalk. AppleTalk at the beginning, when the first Macintoshes were released, was not using TCP-IP at all. And for 10 years, the Macs were running without TCP-IP at all, practically, except if you install TCP-IP to do interconnection with an IBM mainframe, for example. But as long as you are working with Apple-only systems, which many Apple freaks tend to do, you did not need any TCP-IP. And Apple worked exactly in this way. When the Mac started, it would get a prefix from the router, and it would take its own name chosen from the name of the computer. Now the details are, as I mentioned, complexified by the immense possibility that exists to do this simple thing. Here are, for example, three different ways. I mentioned the fact that we could get as host part the MAC address. That's one of the possibilities. Another possibility is to do it randomly. And a third possibility is to do a cryptographically secure address that we'll discuss in a few more minutes. The most common part is to take the MAC address and transform it into the host part. The host part typically, not invariably, but typically in IPv6 is 64 bits. The MAC address is 48, so it's very easy. You could simply take the 48 bits and put it in the 64 bits. That would be too simple if it would be this way. So what you do is more or less this, but you pad it in the middle instead of at the beginning or at the end with FFFE. So this is how many bits? 16. It's 4 hexadecimal digits. It's 16, which is a difference between 64 and 48. And then there is a dirty trick somewhere. You invert one of the bits. So the 7th bit, for some mysterious reason, has a meaning. It's called it's the locally or universal bit. And so the 7th bit of this, 08, is flipped and transformed from 0 to 1 or from 1 to 0. So if you have 08, that becomes 010, 08. Right. That's a detail that we can ignore in the first approximation. Essentially what we're doing is we're taking the MAC address, we expand it in a completely algorithmic way to create your 64 end user host part. You can read that offline to understand the mysteries of why we need to flip a bit. This is not essential. Now another part that is done, typically all systems that allocate an address automatically will perform a kind of test to verify that no one else did it. I mentioned already that IPv4, there is something a bit similar, which is called the link local addresses. That happens if you have really no DHCP and no router, nothing in your environment. Typically Windows systems will boot and pick an address that is valid only link local, cannot be routed. And those addresses are picked randomly. But if you pick an address randomly, some bad things might happen. What kind of bad things? Two devices on the same address, right? If you have two devices on the same address, this is a typical case where networking will break. You will have packets that are inserted into flows, so you will have all protocols practically will have problems. So one of the key things, if you want to attack a network, by the way, that's a very simple thing to do. You insert 4 devices that copy the address of other systems. And if you don't want to attack, you want to avoid this. How can you avoid this if you don't have DHCP server? The goal of the DHCP server is, of course, to avoid this. You give an address to somebody who has this MAC address, and the MAC address is in principle given by the hardware, and you trust that the hardware manufacturers don't play dirty games of giving the same MAC address to different devices. Although This is not totally excluded, but in principle, that should not happen. How can you avoid this if you pick your own MAC address, your own address when you boot? Well, a simple way is to broadcast a message to everyone saying, I have taken this address. Does anybody have it already? And if someone has it, you will probably get a response, and you will detect the collision. It's not entirely safe, but in particular with mobile systems that may be sleeping, but this is how it is done. Now with IPv6, we never broadcast. That's one of the peculiarities of IPv6. With IPv6, broadcast is taboo. Whenever we have to broadcast something, we send it to a multicast address. Question?
How difficult would be, in practical terms, to spoof the MAC address as well? So let's say we do some Slack algorithm and we actually manage to convert that to be something else.
So the question is, how difficult is it to spoof a MAC address? And the answer is, it's very easy. When you do it in the lab, you will see that you can change the MAC address of your interface. So the answer is, it's very easy. Right. So, of course, what does that mean? It means if you rely only on addresses for security, you're in trouble. So what enterprise networks do, they typically observe the MAC addresses. So at EPFL, all the MAC addresses of all the systems that exist are monitored everywhere. If you see a collision, for example, you will flag something somewhere. If it happens on the Wi-Fi, I guess nothing happens. But if it happens in a lab or on a server, the manager, the system manager who responds for that, receives a mail saying there was a problem with this address. In more secured environments, typically a bank or an enterprise, every laptop that we give to employees is registered with its MAC address, and only this MAC address can speak inside the company. Doesn't entirely solve the problem, but this is how you try to solve it. We'll talk a bit more about that security and MAC layer a bit later. Right now, with Slack, this is how a host will acquire its address. So assume, for example, a host boots with IPv6. The first thing it will do is acquire a link local address. With IPv6, there is a special prefix, FE80. That means that's a link local address. I don't need a prefix. It can be used only in the local area network. The only thing I need is the host part, which you get, for example, by taking the modified EUI that I showed in the previous slide. And then you broadcast, or more precisely, you send it to a magical multicast address, this address, which is called the solicited node multicast address. That's a multicast address that is, it's really a low-level optimization of IPv6, and it's those kinds of things that make IPv6 a bit complicated. You could really wonder whether you could not simply broadcast it, but no, you don't. What you do is you create, as explained here, a special multicast address that takes the last 24 bits of the target IP address. The target IP address is the address for which you're trying to do a duplicate test. So you want to reach all systems that have this address. How do you do that? You create a multicast address that has the smaller bits of this address. Why the smaller bits? Because you think that the way addresses are allocated are typically that the least significant bits corresponds to the most specific part. On the same subnetwork, different machines probably have different ends. The last 24 bits are different. So you create a multicast address by taking this prefix, which is reserved with 104. So that means you have only 24 bits to fill in there, and you take the last 24 bits of the target IP address. So here is, for example, our target IP address. This is how we write it normally, compressed form. If I uncompress it, I add all the necessary zeros. I focus on the end. The end corresponds to, I want the 24 last bits. That means the 6 remaining hexadecimal digits. Here I've padded all the zeros to make it truly uncompressed. And then I take this prefix that I have painfully written with all the zeros, and those are hexadecimal zeros, the binary zeros will be even more. and I take this last 24 bits that I add here. Now I compress it, and this is the IP address. Of course, the computers don't compress. They write this with all the bits. But this is what we see here. This is sent to this address. Now, if the last bits are those, this is what we get at the end. So normally what happens is the systems that have this address, they have to register to this multicast address. Multicast is a different way of communication that we've already mentioned a few times. To receive data for multicast address, you need to express your interest, register, subscribe to this address. So any IPv6 system must subscribe to the address, to the solicited node multicast address of all the addresses it has. So if things are okay, if you send this to this address, if anyone else has this, they will know and they will respond to you, I have the address. There might be a collision. There might be another system that has a different address, which is not this one, but has the same 24 terminal bits. That might happen. If that happens, this one will be annoyed a bit by receiving this multicast. He will read the message and will say, somebody is trying to have to check this address. Oh, it's not mine, therefore I will not respond to that. The hope is that that happens rarely, because the probability that in the same local area network you have many systems that have the same last 24 bits should be small. And once this is done, then this host has a valid link local address that it will keep. Now, every interface starts by doing that. If you use Slack, it has its link local multicast address, unicast address. Then if you want to do something useful, you need to have an EPFL address, if you're at EPFL, for example. So what you will do is you will get the prefix. How do you get the prefix? You can ask the routers. The routers on your, if there is no router on your link, there's no point having a prefix. So if there is a router that is going to be your default router, your default gateway, then you can talk to it. So what you do, of course, you don't know yet its address because you have not yet been configured. So what you do is you send a multicast to all routers. So this prefix means all routers that are on link with me, that are in the same local area network. If there is one router that's configured to handle this protocol, it will respond and will give you the prefix and will also give its own IP address so that you will know what is the IP address of your next hop router. So at the end of this process, this machine has also a global address with the here EPFL prefix and its local host part. So that's the basic of Slack. So Slack is very often used. There are variants of it. In particular, some people have expressed concerns about the MAC address being part of the IP address. What's the problem with having the MAC address being visible in the IP address? Well, it's like having a cookie on all your IP packets, because the MAC address is a signature of your device. Probably if you go with your same smartphone in various places, you always have the same MAC address on Wi-Fi, for example. So that means different sites can track you and say, oh, I know this guy, I know this MAC address, I've already seen it. I can sell them some ice creams or something else. So if you want to avoid this, some proposals have been done to do the same thing, but pick random EUIs. Instead of deriving it from the MAC address, you do the same thing. You randomly pick one string of 64 bits. Now, this string is so long that the probability of a collision is minuscule. You still do a duplicate test, and if the duplicate test succeeds, then you get this address. Of course, if you keep the same address as long as your smartphone lives, so for 3 to 5 years, that doesn't help. You're tracked with this address. So what you need to do is to regularly change it. So every few hours, you change your IP address, which means that you have to manage the change of address, which is one of the concerns with TCP. TCP typically does not like that. When you open a TCP connection, for example, you're watching a YouTube video, and that's in the evening, it lasts 3 hours. If you change your IP address in the middle, the TCP connection will be broken. No big deal, but you will see something happening. Yes?
How does TCP know about IP? Because it's like in an IP packet, it doesn't need to know about routing.
So the question is, why does TCP know about IP? Because after all, TCP is a layer above IP. What does it know? Well, TCP doesn't know about IP in the sense of a protocol. It doesn't care about what routers speak together, but TCP uses the IP service interface, right? So TCP needs to know what to do with the segments it creates. It needs to send it to an IP box that has a given IP address. So it is connected to a given service interface. Right? If this IP address disappears, for example, TCP was receiving data from a given IP address. If that IP address disappears, then TCP receives nothing. So the application will need to do something. You will see in lab 3, when we use TCP, we see that even though the thing is nicely layered, in the practice of programming, it is not layered. When you have to, well, it is layered in the sense that we don't see the MAC layer, but the layer IP is visible in the sense of IP addresses at the application layer. Right? You go to a server, and for that you need to give the IP address of the server. Of course, if you use this, you would not do what I said. You will not break the YouTube video TCP connections. If you're using TCP, you will see that Google has invented a way to go around the problem by not using TCP for YouTube, but that's for later. If you use TCP, you don't want to change the address. So you allow to have, with IPv6, to have what is called addresses that are a bit stale. They're a bit old, but they're still in use. They're in use because there are TCP connections that are still using them. As long as those TCP connections are not killed, you keep those addresses here. But whenever you do something new, in particular when you open a new TCP connection or you send a packet using UDP to some DNS server, you don't use this source address. So we see that a side effect of this is an IPv6 machine routinely may have several IP addresses on the same interface. Whereas in IPv4, it's quite pathological. It doesn't normally happen. In IPv6, that's quite routine. It has already two addresses, the link local and the global address. Plus, if you use that kind of things, you might have some deprecated addresses that are still used, which makes the debugging a bit more complicated. Now, the thing I said before, called Slack, has a little bug that it doesn't give the DNS server address. Right? You get all the IP configuration, but you need something else, which is the DNS server address. So, or you could say, you could go to ITF and say, oh, come on, go and fix the bug. And the bug could be that, for example, in this thing, the router that knows also the IP, the DNS server. I mean, this is a machine configured by your system managers. You could respond with not just the prefix, but also the IP address of the DNS server. It could do that, and there are proposals to do it. An alternative proposal is to use what is called stateless DHCP. The only difficult thing is really to understand. If you see this and you read the Wikipedia page, you know, why is there stateful and stateless? What does that mean? So stateful means there is state, means there is a table somewhere, a database, a table, a file that has information. What is that information? In the case of DHCP, it is the mapping IP address allocated to whom? To which MAC address? Be careful, that's not a mapping used for routing or anything like that. It's just a mapping for management. I am the DHCP server. I have given this IP address to this smartphone that had this MAC address, and I remember that, and this is marked in my big table. So we say it's stateful because this is remembered somewhere. State, and also the DHCP server typically will verify a number of things before giving you the address. For example, if one or several addresses in your subnet is pre-booked for servers, then you will not get it. So it really needs to go to this table to know what to do. This is what we call stateful. You need to go and see some information that has to be permanent. If the thing crashes, hopefully the information is stored on disk so that when it reboots, it gets it again. So that is what we call stateful. In general, in networking, we try to be as little stateful as possible. Stateful causes a lot of problems when there are crashes or failures. In particular, if you're changing a state and you crash while changing the state. It's like if you switch off your PC or your Macintosh and you don't have journaling on for the file system, you might have corrupted files. That's an example of problems that go with stateful. So if you have stateful things, you need to do a large number of things to go around all the problems caused by the crashes. A radical way to avoid the problem is to be stateless. Stateless means whenever you do the thing, if you reboot, you start from empty and you will collect your internal state from the history of what has happened, and there is no need to be consistent from one time to the next. Slack is stateless. When I boot my computer, I will get an address, and this address, there is no table, at least no software table written in software. There is a state information, which is my MAC address, for example. But there is nobody is keeping state about what to say to me. And if I use randomly assigned addresses, I will have new addresses whenever I reboot. However, as we said, you still need to have the DNS server address, so that needs to be provided by an additional mechanism. And the mechanism that is very often used today, if you use Slack, is to still use DHCP, but now you use DHCP in a static way. The DHCP server simply knows what is the IP address of the DNS server. Now you can say this is state information, and it's true, but it's not state information related to you, to the thing, to your address, for example. This address that will be returned by the DHCP server is always the same. It's the IP address of the DNS server. So that is why it's called stateless DHCP. Voilà, so those are all the kind of complexities. As I mentioned, instead of this, you could have the router do it, and, but this is not much done today. But hopefully it will be done soon. Here is another more typical use of DHCP for the places in the world where you have IPv6 on DSL modem, for example, or where your public provider gives you an IPv6 service. Then if you are your home router, for example, you will receive, you can use PPP, or if you're more modern, you can use DHCP and get from the DHCP server of your provider your own address. You want your own address, and that's all you do with IPv4. But with IPv6, we want more. We want my address here, because I'm part of the Swisscom network here, or Simpscom network, sorry. But also, as an edge router or an ADSL modem, you also have the job of managing the addresses in this network. Typically, this will have the DHCP server for your home network, and you have to give the addresses for your subnetwork. At home, you probably have just one subnetwork. If it's an enterprise, you may have multiple subnetworks. So what is the most natural thing to do if you're a provider, ISP provider, and you want to manage this? Well, you give a prefix to this guy, and this prefix is, for example, 2004 AAA BBB CC, which is almost everything except the last 8 bits. So that's a 56 prefix, 56-bit prefix. I give this prefix to this guy, and then they can use it to make here 2 subnetworks. So a small optimization is, well, what about the address here? If we do it the IPv4 way, this address is one IP address that I get from my provider. The address that I give here are completely different in IPv4. They are private, right? Here, it's a smart thing to do is if this address belongs to the same prefix here. Why is that a smart idea? Well, because by giving, if I am the provider, I give this prefix 2004 AAA BBB CC to this guy, and I say your own address also belongs to the prefix, and all the addresses of your enterprise, of your home, also are within this prefix. That means for my network here, I have only one prefix for this entire stuff. So in my routing tables, I will have only one entry. Whereas if I would give one IP address to this and one prefix to those, I need to remember that a packet that is going to the router, not to the host, but to the router, has to go to a certain entry given by the routing table entry. So I will need one routing table entry for this and another one for this prefix. So this obvious optimization is done, and it's called DHCP with delegation. DHCP with delegation means that if you use IPv6, your ADSL modem gets an IP address from your provider, but it gets not just an IP address, it gets the IP address plus the right to use one part of the prefix for your own usage. And by doing that, we perform aggregation here. If we compare to IPv4, what are essential differences? This is possible only with IPv6. If I compare to what is traditionally done with IPv4, what are the differences? Yes? With IPv4, here we would have a NAT. With IPv4, you get one IP address of SIMSCOM, and all your devices at home, they don't have SIMSCOM IP addresses. They have private IP address. And since they have private IP addresses, this box has to translate them and becomes a NAT. In IPv6, the dogma is we do this. We do this here, and by doing this, NATs are no longer used. So IPv6 has two taboos, broadcast in the local area network and NATs. So the IPv6 developers, they believed very strongly that NATs would not be needed. And in fact, when we started the Internet Engineering Workshop 5 or 6 years ago, we still wanted a NAT, because when we are in this room with all our computers doing routing protocols and weird things, if any of you does a mistake, you might leak routing information into the rest of EPFL, or if one of you is even very nasty, then you could start an attack. So we have to be separated from the rest of EPFL. NATs provide a means of separating the address space that we have in the room. Is completely orthogonal, does not belong to EPFL. So first, it's very easy to track what happens, and it's more complicated to do attacks. And we looked for NATs, and at the time we did it, 5 or 6 years ago, we didn't find any open software that was doing NATs for IPv6. And one of the reasons I attribute to this dogma that this is how we do it. NATs are to solve this problem in IPv4 that doesn't exist in IPv6. Therefore, nobody did a NAT for IPv6 to IPv6. In the meantime, you find some NATs for IPv6. They are called NAT66, which shows that this is not a sufficient argument to do away with NATs. The need for privacy and also the need for separation of addresses is certainly present here. So I mentioned the fact that multiple addresses are the rule with IPv6. So very often you need a way to identify an address. So practical thing, when you look into the routing tables, you need to give not only the IP address, but also the routing table, which in IPv4 was not necessarily. From the IPv4 address, if you're a router in IPv4, by analyzing the address, I can know on which interface this next hop is. On IPv6, that doesn't work. So different operating systems have different tricks. In Windows, for example, we use this sign, and we find it also in some versions of other operating systems. It's called a zone index. It simply means if I am a router here, and if I have link local addresses that I use in my routing table, I have to express on which port they are, which is given physically here. I'll skip those that we have seen. So to wrap up on this avalanche of low-level details, here is a quick question. I close the poll in 5 seconds. And the obvious answer is D here. So it gets everything. One more. I close in 5 seconds. Ta-da. And the majority is right. Last question with Slack. I close in 5 seconds. And the answer is A, which is a difference with IPv4. In IPv4, you get a link local address only after trying to get an address by all other mechanisms. And only then, if it fails, you get a link local address. IPv6 does the other way around. First, you get an IPv6 address so that you can talk to other systems using TCP-IP, including talking to DHCP servers. So that's for address allocation. We'll talk a bit more about address allocation with cryptography in a few more minutes. But before now, let's move on to a closely related topic, which is MAC address resolution. So what's the problem? The problem is, as we have seen it already, when an IP machine needs to send a packet to next hop B, so B can be the final destination if A and B are in the same LAN. Otherwise, B is a router on the path from A to the final destination. A can also be a router that is forwarding to the next hop router. But to send a packet to B, you need to find the MAC address. Now, how do you find the MAC address? That's the question that we see here. So how is that done typically? Typically, on Ethernet, at least, is done by broadcast. A sends an address resolution packet on the LAN that is sent to everyone. Modulo, of course, in IPv6, we will not do broadcast. We'll do something similar. All hosts that have the IP address of B respond with their MAC address. So we ask everyone in order to get one answer. And this is called Address Resolution Protocol, ARP. So here's how it works in practice with IPv6. With IPv6, everything is the same as IPv4, but the acronyms have become longer. Well, it's like the addresses have become longer. So ARP is called NDP-NANS. So NDP stands for Network Discovery Protocol. I'll steal 30 seconds of your break to finish this slide. So I said that normally, so A wants to speak to B. So A knows the destination address of B through some mechanism, through DNS or by responding to a server query. Then, so it will broadcast, between quotes, a packet that is called a neighbor solicitation packet. Now, this, of course, is not broadcast, but is sent to this address, which you recognize as a solicited node multicast address. So you send it to the target address. You want to speak to whoever has this address, but you cannot send a packet to this unicast address because you need to know the MAC address. Now, as we will see when we talk about the MAC layer next week, for multicast, you don't need to have the MAC address of the destination system. So you can send a packet to this multicast address, and this is done by having a well-known MAC address, which is algorithmically derived from this one here. So B, that owns this address, must listen to that. That's what we said already. It does it for duplicate test. It does it also for ARP, for address resolution. So B will receive this packet and will respond to it by saying, yes, that's me. I have, and it will respond with a packet that gives the MAC address. So if you want, this packet is an address resolution reply. It's called a neighbor advertisement and is sent by B to A. Voila, we'll do a break and we'll continue analyzing this at 1:15.